Hi, so my name is Alex Bolazel. I'm here to present my research on reverse engineering Windows Defender's JavaScript engine. So a little about me. I am a researcher at Riverloop Security, 2015 graduate from RPI and a proud member of RPI Sec. Longtime Recon attendee. I've been to the past 4 Recon Montreals. This is my first time presenting though, so it's really an honor to be here. And I've done some prior work on antivirus emulators called AV leak, you might have seen. Doing some side channel attacks to find ways of evading and detecting them. And this is sort of building on my background of reversing AVs. There's my Twitter, if you want to follow me, talk to me, whatever online. I think I have open DMs. All right, so an outline of this presentation. I'm going to go through an introduction, then talk about tooling and process, then the actual reverse engineering and the results and what I observed within Windows Defender, a bit on vulnerability research and potential vulnerabilities and attack surface that's left in there, and then a conclusion. So the motivation for this research, for digging into Windows Defender's JavaScript engine, was you may have seen this tweet from Tavis Normandy in May, where he found this crazy bug. Turned out that bug was in the Windows Defender JavaScript engine, and that really got my interest. I hadn't really written JavaScript since I took a web dev class in college. Had really interested in reversing JS engines and learning more about those and browser exploitation, that sort of stuff. And I also had this background in AVs and reversing them, so it was a natural fit for me to want to have this interest in learning about JavaScript engines and have this background with AVs. And then this was sort of this hot topic. Windows Defender's JavaScript engine, why is it there, how does it work, what's going on in there. So I started digging into it and just spent a while reversing it. So Windows Defender is Microsoft's built-in antivirus. The term Defender now seems to cover like any security system built into Microsoft like Windows. So you have like Defender this, Defender that. In particular, we're talking about the original use of the word Defender, meaning the Defender antivirus product, and in particular, MpEngine.dll. So the reason this is interesting is as a target for exploitation or vulnerability research, runs a system, it's unsandboxed. So if you get RCE, instant prevesc, you're also running inside an AV context, so you can do whatever you want. Very high privilege, they're probably not going to detect themselves doing anything malicious because they are the AV. And it's built from a bunch of scanning subsystems. This presentation just hones in on the JavaScript subsystem and the scanning routines for JavaScript, which is about 2% of the total code within Defender. It is absolutely massive. I think 11 megabyte large DLL, 45,000 functions. We're just looking at this 2% that is the JavaScript engine. So modern JS engines are generally open source, very complex. They have things like JITting, optimizations, all sort of stuff. And they're often integrated with web browsers or sometimes with things like V8. And generally, if you want to do a vulnerability research against them, you can just go read the code because it's open source. In contrast, Defender's engine is only distributed as binary. Best I can tell, it's not integrated or stolen from any other code base. It seems to be in-house built and sort of proprietary to Defender. And it is complex, but it's at least tractable to reverse from binary. It's not doing a lot of the stuff and the complexity of a modern JavaScript engine that would make that harder to reverse. And it is standalone, but has some minor browser emulation. It's not integrated with the browser. So that covers the introduction. Now moving into tooling and process to talk about how I did what I did. So first off, scoping out what we're looking at. Every month, Microsoft released this thing, mpam.fe, or /fe.xe. This is kind of the update for Defender. It includes MpEngine.dll, which is basically the core of the Defender antivirus product, as well as some signatures and these VDMs. I presume that's like virus definition module or something like that. I don't know exactly what that stands for, but that's what I think. Seem to be related to like signatures and also stuff that gets plugged in. So there are certain features of some of the emulators and the scanning routines that are dynamically plugged in, kind of at runtime. They're loaded from the VDM files. Defender is released about monthly. I started tracking it when the Project Zero bug was dropped. I started pulling down Defender builds, and this is the schedule I found, at least for the 32-bit builds. There are also 64-bit builds, but I was really working with the 32-bit one, and that's what I was tracking. You can see there's been like some lag and some delays. In December, the UK released like a bug report to Microsoft, so there was a little maybe delay in getting that out. The latest build came out January 18th. So in terms of tooling, did a lot of static reverse engineering with IDA. What's nice about Defender is they do publish PDBs, so you can work with those. Doing some bin diffing, using both bin diff and diaphora, and also dynamic analysis with a JavaScript shell kind of harness and WinBag. So in terms of static analysis, as I said, this engine is really large, about 45,000 functions. The JavaScript engine is only about 1,200 of those 45,000. And what's really nice is that Microsoft actually publishes PDBs. So you see here all the symbol names, the function names. You know, I'm so used to loading things in IDA and not clicking do you want to search at the symbol store? If you actually load this in, you'll pull the symbols down. They're published, it seems, about 3 weeks after the release of the actual update. But it's really nice to have, thousands of symbols. There are also some leaked builds that have more information, for example, type information that can be useful. But that's just, icing on the cake to have the types as well. For dynamic analysis, I used a shell. So this was kind of a REPL, read eval, print loop kind of thing, where you could give it a line of JavaScript and have it be evaluated. The way this ended up working was that it actually doesn't maintain a state. So each line you put in kind of is its own line. You can't necessarily define variables and use them again. So each line is kind of self-contained. That's why you'll see this format with the parentheses, and we're basically just defining this one function in one line, just running it right then and there, and you can see it printing out results from here. Now, in terms of building that shell and why we had to do that, it's really difficult to work with products like this, with antivirus products that are so complex, so large, that may be protected. For example, Defender is a protected process. So you can't just attach a debugger to it in Windows, even if you're admin or system or whatever. There's different solutions. Halvar proposed going and using a kernel exploit and just flipping bits in the kernel. Tavis wrote a shell. Huxian and Elias in their book proposed just building custom loaders. This is sort of what we did. Another problem, in addition to just the fact that it's a protected process and it can be hard to debug, is that code reachability can be based on heuristics. It's not necessarily easy to just say, here's a buffer. I want you to scan it and go down these code paths and guarantee that it's going to run in the JavaScript engine. So being able to trigger on demand and know exactly that what you give in will be run as JavaScript, that's really helpful for this sort of work. So the solution is to build this custom loader and then call directly into functions that initiate scanning, the actual JavaScript scanning routines, rather than worrying about all the heuristics that look at the code, try to determine if it's worth analyzing, things like that. Just call directly into those scanning routines. So this was a shell that we built. Just to talk a little bit about this. The focus of this presentation is more on the reverse engineering, but just talk about how I did a little bit. There was this guy, the Wackolian on Twitter. He dropped the shell shortly after Tavis did his bug. And then Rolf Rolls and I were looking at this together and ended up building a shell using some of the techniques that this guy used, but doing it in C. He had released a shell in C#. I found it wasn't very stable. It crashed some on me when I was trying to just work with it within a couple hours. So I wanted to have something more stable and be able to instrument it ourselves and do whatever we wanted. So Rolf actually did most of the work on this part. I helped out with this some and extended it. But basically, we're going to patch. There's this object.js runtime state that is basically the entire context for running the JavaScript code. So we just patch the constructor and provide a custom vtable. And then throughout the engine, there are callbacks that are triggered, basically to provide the AV portion of Defender with some ability to do introspection on the malware that's running inside of it. And we just patch those basically and provide an implementation. And whenever the print function is called in JavaScript, the AV Defender section gets kind of a callback that says the malware called print. We provide an implementation that says if you called print, let's just print it to standard out. So to show this kind of in a diagram, we begin with a Windows binary here. This is the actual loader code. Load library on MpEngine.dll. Within there, you have the JavaScript emulator. Again, this is about 2% of the code, but so it's not to scale. Within there, you have this function JavaScript interpreter eval. That's kind of a main entry point for evaluating any JavaScript statement. And then it constructs a JS runtime state, which is this large object that represents the runtime state of a particular JavaScript statement. We add this custom vtable to it, and then provide a callback that when the print function is called and you get this AV callback to look at this event that just happened, we're going to print that to standard out rather than letting the AV handle it. So this allows us to have some introspection, see what's going on inside the engine, share information in and out. And then we just give our code in, and it's going to get scanned and run out. And then as we call print, we can print stuff to the terminal. Because we did this on Windows, and it's just native binaries, and we're calling load library, we get WinBag integration, which is really nice, particularly having those PDBs. We can do anything WinBag can do. I really like WinBag. It's a very powerful debugger if you know how to use it right. And you can do things like print out objects. You can see here the DT MpEngine JS object. Get nice call stacks, even when you have things like optimized functions that are optimized out or whatever it may be. Custom calling conventions, whatever. So this was really cool. In comparison, some of you may be familiar with Tavis Ormandy's load library. So Tavis built his own system to do this, and just wanted to compare our approach to his briefly. He published this up on GitHub, and his approach is slightly different. Obviously, he was doing this on Linux, which is really unique, and just exposing the engine in a sort of different way. So just to walk through that briefly. Tavis begins with a Linux binary, does his load library thing on MpEngine.dll. So this is a Linux PE loader that he wrote. And then he provides some Windows API emulation, resolves imports in the IAT to his kind of shimmed out Windows API implementation for Linux. He has the JavaScript emulator. And then there's this function, JS delegate object global parse float. It's basically the parse float function. So if you call that, that takes a string that has a floating point number and converts the string into an actual floating point number. That ends up resolving to a call to strtod, which is just the native C runtime function to do this. And Tavis just hooks that, and basically if the string you're supposed to convert to a floating point number is prefixed with a certain prefix, he'll print to the screen. And then he just passes his input in through the main kind of entrance for all scanning R signal, which means he has to pass through all the heuristic scanning things that try to determine if this is worth scanning, if it's malicious or not, is it worth actually emulating. So he appends a bunch of highly entropic JavaScript and HTML and CSS to the end of his payload, and that's a way of kind of getting around that heuristic, making this look like a very complex thing that may or may not be malicious and is actually worth scanning. So this is the engine you may be more familiar with, this loader. So here's just kind of a comparison, how his system works versus ours. And you can check his out on GitHub. So just a demo to show that this works. This is just a Chromebook I have here. I don't have my full dev system here, so I did some recordings of myself using the shell. Just to print hello. Let's see. Sorry, it's on the other screen. So this is the shell in action. So you can see that we gave in some code called the print function, and you'll see it actually prints it to standard out so that we can see what's going on inside the engine rather than just having it sitting there kind of in a black box. So just a demo to show that that works. All right, so moving into talking about reverse engineering the engine and what we found inside of it. Does anyone have any questions at this point? All right, so kind of overview of this section. This is kind of the main part of the presentation. Going to talk through first the JavaScript language implementation within the engine, then some on the types and JavaScript types and objects that they have implemented, then a bit on memory management and how that's implemented, and then I'm very interested in finding ways of evading antivirus emulators, little tricks you can use to detect them and get around their scanning. So I have a bit on that. So moving into talking about the JavaScript language itself. First off, Defender's JavaScript engine, best I can tell, it's proprietary. There's no shared code with other engines. So it's not based on things like JavaScript.dll or Chakra, or any other engine that Microsoft has built to do JavaScript. At least from looking at symbols, any strings, any information like that, I haven't been able to find any overlap with any other Microsoft products. This seems to be wholly built in-house by the Defender team. Generally, there's a focus on JavaScript language implementation, so just providing the actual JS language and not a full browser emulator. There is a small browser emulator and some DOM emulation, but they're not doing all the complex things that a browser would do, what interfaces it would allow JavaScript to use to talk to it and manipulate objects and things like that, and DOMs. Code is all interpreted. There's no JITting, so they never have a JIT engine, anything like that. It's written in C++, single-threaded. Because this is an antivirus emulator, it's time and memory constrained, so it can only scan for how many seconds or milliseconds, and it can only use so much memory. If you exceed either of those, they'll just kill the process. And there are also, as I said, analysis callbacks throughout this engine that inform the AV portion of Defender what the malware is doing, how it's behaving. And again, it's about 1,200 functions, rather. You can see here some configuration stuff. Because the engine, the AV users might want to configure the engine. They have heuristics like you can set, max script size, minimum script size, number of variables you can declare, number of times you can call garbage collect, so forth. This is all configurable by sort of the AV portion of Defender that they can set up the way they want to scan to run. The language implemented is roughly ECMAScript 3, so they don't have a lot of modern JavaScript language features like things like ECMAScript 6 has, but the core of kind of what JavaScript has is there. So you can see here the two columns, implemented and not implemented, what they have, what they don't have. I'm not an ECMAScript expert. I emailed Natalie Silvanovich from Project Zero, who did some of this initial research and was talking to her about this. She said it's kind of roughly ECMAScript 3, but doesn't have the whole thing, and that's sort of what I found. Basically, it's roughly ECMAScript 3, so the core of JavaScript, but none of these fancier modern features. I did find it was interesting that the switch statement they implemented, but it's actually broken. Fall-throughs don't work, so this is just kind of a unique eccentricity of this engine. It's not like a full-on engine ready to be used in a browser or something like that. There's like some weird bugs like that. And I have a demo showing how the switch statement is broken. That was just from my reversing, I found that. So first thing, how do they actually parse the JavaScript code and understand it? There's this structure NDN parse data that's used throughout the JavaScript engine for parsing stuff, whether that's HTML, the regex parser, and also parsing the JavaScript language itself. So basically, they populate this structure with a bunch of function pointers and some configuration data. So here you see it's ECMAScript-specific parsing functions that they're going to use to parse through the data, parse through the code, rather. And after the code is parsed, they pass through this function JSTree_run that actually takes evaluated tree of code, AST, and is going to run that. And this function can be invoked multiple times as we go through the engine. So for example, if we call eval and we pass it a string, it's going to have to parse that string and then run it. If we have like a toString method, for example, defined, they'll have to parse that and run that. So you can see here, like AST to program tree, they're doing these conversions and then running what they've converted, what they've parsed out from the code, from the AST. And then various eval functions. You can look for these functions that have eval in the name. These implement the actual evaluation of particular JavaScript statements. So a switch statement, a for loop, a variable declaration, they're all implemented in these functions. Again, there's no JITting, it's just interpreted statement by statement. Just show an example stack trace during a callback. As I said, the run function being invoked multiple times. We begin with the call to eval, then run, and then they're evaluating. So this is kind of the outer, the whole function being evaluated. Then as we allocate a new string, you can see the call to the string allocator, creating a new object of type JS string object. And then because we're calling new string on X, we need to invoke X's toString method in order to create this string. So then that's getting called here. And they're actually going back, parsing out the toString function, and then running it, evaluating it. I have put a breakpoint on isnan, so there's actually now a call to isnan, and you can see that here we are broken on the isnan function. Because isnan is kind of a globally declared function that's just part of the JavaScript language, the way it's implemented is basically declared as a global variable. So you can see here it's in this JS delegate object global namespace with all these other global functions that are accessible by anywhere. There's also a regex engine, just wanted to touch on this. This is accessible from JavaScript. Best I can tell, it is, again, a proprietary engine. I couldn't find any of these symbols or function names or strings anywhere else, Googling around for them. This is obviously a really big attack surface. I think if you went and fuzzed this, you'd probably maybe find some good stuff. Doesn't seem like a good idea to have your own custom regex engine in this unsandboxed system privileged engine. So you can just pass in strings like, hello Recon here, and then this is going to pass to the JavaScript engine. You can see here it's broken. They're compiling actual JavaScript statements, running them, evaluating them, so forth. This is a stack trace that I've broken in here. As far as the antivirus integration goes, there's this structure or class called nscript JS monitor that implements callbacks that are used to monitor execution for the antivirus purposes. So when you call specific functions, when you create a string, when you do a toString, any action you take, they're going to call this function and inform the AV side of Defender what function you ran, what's going on, what are you doing. And again, this is the sort of facility that we hook in order to be able to print data out to the screen. You can see here, for example, if you call setDate, they're going to have this callback that the event you did was a date setDate. If you call value of on a Boolean, they'll call these functions, and depending if it's true or false, they'll tell the AV set of Defender. So this is going to inform any sort of heuristics they might have for matching malicious JavaScript, or if they know that a particular sequence of API calls is known to be in some piece of malware or some exploit or something like that. This is how they're kind of getting informed. I didn't dig too much into the signature side of this. I was focused more on the JavaScript side, but just to talk through that, how that works. The JS runtime state is this giant, basically like singleton, huge object that is the entire JavaScript state. You can see all kinds of stuff here, whether that's the JavaScript heap, the stack, the variables that are declared, the globals, everything. This one structure represents sort of the entire JavaScript state, everything you need to know about a particular execution as it runs and provides all those facilities. So this is a very important structure in this engine. So that kind of concludes at least the JavaScript kind of internals portion of this talk. Moving into talking about types and objects and the facilities that it provides for that. Does anyone have any questions at this point? All right, no questions. So first off, JS object is the parent class for all of these JavaScript objects. So this is kind of JavaScript complex objects. We're not talking about primitive types like raw strings or numbers, but any complex object is going to be this or some kind of object that's subclassed from it or inheriting from it. We're going to talk through some of the specific fields and what they mean, how they work later on in the presentation, but just to introduce this. As I said, there's lots of different subclasses, lots of subtypes that can derive from this. There's an enum JS value type that defines various types that are implemented in the engine. Not all of them are actually used. Some of them are just present in the PDBs. So for example, the date type isn't actually used. They have a date object, but it doesn't actually use this type. It has a different typing method we're going to talk through later. But just to show you sort of what types and things this engine supports. And as I said, all the different object implementations can inherit from that parent class. So you'll see here they added on length prop hash. So this is basically a hash of the string length for an array, because that's something that's every array is going to have is a length. So they wanted to add this one field to it. They may add functions in the vtables, things like that as well. Or if you have a regex objects, they're going to have the pattern string that you're searching for, and one other type that unfortunately is cut off on the projector, one other element of this object. So again, they can extend these objects to provide specific facilities for individual subtypes. And then you also have things like the date object. It doesn't actually necessarily inherit from JS object, but what it does is they set the value pointer to point to another structure called a JS date, and they also set this class pointer to point to the string date. So anytime they actually want to work with a date, rather than checking the particular enum for the value type, they're going to instead check the class string. And as you can see here, this is basically any function that works with a date. They get this pointer to this object, and then they need to validate, is this actually a date or is this some other type? So they're going to do that by actually doing a stir comp on the class string to date, and then converting the actual pointer in M value here to a JS date, or grabbing that, casting that. So various different ways that they implement different objects and different types within here in memory. There are also various string primitive types. So these are 4 different ones. These are all primitive strings, so not full-on objects. Various styles they have. So if you concatenate strings, they'll construct a concat string. If you take a slice of an existing string, that's going to be a substring. Buffer string is just a raw character buffer. Or if it's, say, an error message that is already programmed into the engine, they can just give you a ref string that points to this object in the .data section of MpEngine.dll. All these various objects obviously have functions and methods that can run on them. So they implement these delegate functions. So when you call string.toString or value of or date.setDate, it's going to get dispatched through these delegate functions. And they use kind of these switch statements, and they have enums that define the particular what particular function it is, and they'll walk through these. There are also a lot of methods that aren't unfortunately implemented in here. These are ones that I picked out from looking at error messages, things like that. So a bunch of things that just aren't implemented, whether they're too difficult to implement, they didn't want to deal with it. I thought with array it was particularly interesting that array.sort and some of these shift and concat ones are not implemented. Array.sort has been a source of a lot of problems for various JavaScript engines and browsers, lots of CVEs from getting this function wrong, because you could have re-entries to the JavaScript state, you could change the length of the array during that, you could change all kinds of things. It's hard to get right, so the Defender developers just kind of sidestep that issue entirely by not implementing array.sort at all. So it just throws an exception that says, we don't have this function. So they really avoided some implementation complexity by just throwing away certain functions they didn't want to deal with. So here's another demo going through some of the stuff that I just talked about. First off, as I mentioned, switch statements are broken in Defender. So here I have a recording in Chrome showing that a JavaScript switch statement should have a proper fall through. So you'll see here we have 2 cases, and we're going to case 0. So when we go to case 0, it's going to print 0, and it's going to fall through and print 1. But in Defender, the switch statement is broken. It only does the case that it matches on, and it doesn't fall through. So if we play this here, we're giving in this input, the same input. Basically, we should go to 0, and then we should print 0, and then we should print 1 after because we fall through. But in Defender, in their implementation of the switch statement eval function, they don't fall through, and they just print 0. So this was a non-security bug that I found. I thought it was interesting, seeing that some of these JavaScript statements are actually broken, don't actually work as they should. The next demo is, as I said, array.sort is not implemented, unfortunately. So if we have an array and we try to sort it, we get a type error, and it says, exception, array.sort is just not implemented. They don't have this function, unfortunately. So as I said, this is a cause a lot of complexity and problems in other browsers. They just don't implement it. They throw an exception. And then the last one is showing some of these analysis callbacks that I talked about, that during execution, Defender can do these callbacks and learn about what actions the code took. So you can see here we're calling this long sequence of functions. It's basically going to resolve into a join of the array, then a parse float call, and then a string value of. And you can see we have this hook that's printing out to standard out when each of these actions are taken, what action kind of was logged to the AV portion of Defender. So you can see here the call to array join, parse float, and stir value of. So just to see, this is the sort of input that the AV portion is getting as your code runs that it can use to learn about the code and detect potentially malicious malware or heuristics that it might recognize. Okay. In terms of type checking and type safety, as I said, there are two fields in the JS object structure, type and class, that are used to define sort of a particular object. What is it type? What is it? So these can be checked with explicit calls to get value type and checking against the enum. So, excuse me, 9 is the enum for a regex object. So you'll see here they're calling that and then casting. If it is 9, they can then safely cast this pointer to a JS object into a JS regex object. They can also do the string comparisons in the class object and check if something is, say, a date, a string, or a number. These are types that are a little simpler, don't necessarily need a full-on implementation. They can just take the JS object and maybe have a value pointer from there pointing to another object or something like that. They don't need to have a whole inheriting subclass. They can do sort of casting. So if you pass in something that is not a string to a function that expects a string, they'll run toString on it and sort of cast it into a string. So they might have, they can have like a pointer to a toString function, or just have this conversion that toString throws. So if the conversion fails, they'll throw an exception. And they also sort of have duck typing. So for all these functions that expect arrays, if you pass on something that just has a length field defined, they can treat it like an array. So you'll see here they're basically just checking, does this have a dot length property? If it does, we can treat it like an array, and if it doesn't, we can't, basically. And in terms of redefinition, I spent a lot of time trying to see if I could get like type confusion or something like that. Obviously, Project Zero found one bug involving type confusion in the error functions. I was sort of looking at that, if we could do things like take an array and then call a date function get month, passing the array as a this object for that call. And unfortunately, I found throughout the engine they're pretty good about doing type checking. So you'll see here they throw an exception. This function can only be called for dates. So you can only pass in things that are dates to this function. You can't pass in like arrays. It just won't accept that. It'll throw an exception. So I spent a lot of time doing things like this and trying to get oddly typed functions into other functions or oddly typed objects into other functions. But they seem to be pretty good about doing this type checking throughout the engine. There is also some DOM emulation, as I mentioned. DOM objects are a special type of object, and all these objects have this mHTML pointer that can point to this iterator, basically, of a vector of HTML nodes. Document is this globally declared object that's there, so you can do document.write, document.whatever, as you would in a web browser. And then there's this very minimal implementation that lets you create and append HTML nodes to the document or whatever it may be. But it's very minimal. Just lets you basically create them and manipulate them a little bit. It's not a full-on browser, obviously. So object properties, so when we have object, dot property, whatever, I wanted to dig into how that works and how that's implemented within the engine. And I found that basically in any JavaScript engine, objects are basically associative arrays that just have particular properties you can define. They can be user-defined and added in at runtime. And in Defender, they're backed by just standard tree, so just using C standard runtime, C++ standard runtime classes. And then talking through how that's actually implemented, they have these sparse arrays for strings and also dense arrays when you have actual arrays, which would show that. And these object properties are only valid for complex objects. So if you have like a raw number that's just a primitive type, you can't have properties on it. But if it's an object, you can have subproperties. So again, showed this struct before. This is the main structure for any JavaScript object. And you have these pointers here, property names, properties, and property array. And to talk through those, the mProperties array stores any non-sequential numeric property, or as well as any string property. So using this as an example, this little snippet of code here, the foo property would get hashed, and then within this table they have the standard tree that would map onto the string bar. Because the array is length 3, so it's 0, 1, 2 indexes that it has, the 12 is a non-sequential property. They don't have numbers from 4, 5, 6, 7, 8, 9, 10, 11. So they convert 12 to a string, hash that, and then store the value ABC there. And then the property array is a standard vector that's used to store sequential values. So in this case, 0, 1, and 2 are stored in this standard array. And this is called dense because it's basically dense. It's one slot memory after the other, where the other one is sparse and they're using actual kind of a map to back it. And then property names maps and stores the actual names of the properties. So you can iterate over particular properties of an object. So you can say like, for x in y, print x, and you can print out all the names of the properties. And in this case, what they do is they hash the name and then store the actual string associated with it at that pointer. So a hash foo and then store the string foo there. So if you try to retrieve x.foo, they can look at that up, look at the property, look if it's there, so forth. You'll see here this function is when they're actually checking if an array is sparse. The way they do that is by checking if the length of the array is greater than the length of what's in the dense array. So it's kind of if it's sparse, basically means that it has non-sequential entries. I wanted to dig into how the property hashing is actually implemented, because I kept seeing throughout the code this calls to genprop hash and then get taking this hash value. So basically this is to retrieve a particular value from the object, and I was interested in how that worked. So I started reversing that, and I found that the genprop hash function is going to call into prop hash stir, and then prop hash stir looks like this. So it looks kind of cryptographic. They're doing some XORing, some loops over the stuff. And I wasn't sure if this really looked secure. I couldn't find these values as say, cryptographic constants online or any known hashing algorithm. It's not like MD5 or any known hashing algorithm. I was interested in how that worked. So I wanted to see if I could brute force a hash collision because it didn't look cryptographically secure. And wrote some Python to do that, and actually was able to brute a hash collision. And I was looking for collisions with the length property. I was interested in that because that's a property that any array is going to have. And I wanted to see if we could mess with the length property and trick things to thinking arrays were longer or shorter than they really were. Maybe there would be some vulnerabilities from that. Found a bunch of hash collisions, but one I'm going to talk about here is the hash of length is the same as the hash of FYW093. So you hit that property and you actually change the length property in this mapping they have of values. I was interested in this because there's a function that is called every time you change the length of an array. And I wanted to see if I could hit this function by not actually changing the length, but changing some other property. Maybe we could, some vulnerabilities or something like that. So I have a demo here actually showing that hash collision working. Okay. So as you can see from this code, basically we have this array of length 3. We printed the length, it says it's 3. We printed the array 1, 2, 3. And then we're going to change, rather than changing the length property, change this property, .fyw093, put it to 5. And then you can see when we print it out, it'll say that value is 5, but also the length is 5. And you can see that here in the video, as this is the same code. So the length is 5, but also this fw093 property is 5. And then this function is going to fire when we update the length. And it'll think that the array is 5 long. So when we print it out this time, we're going to get 1, 0, 1, 2, 3, comma for the 4th element, comma for the 5th element. And then if we set this property to 1, and we print the array out again, we'll just get 1 and length of 1. And you can see that again here in the video. In this case, that now thinks the array is shorter. So this was interesting. No bugs actually shook out from this. But it was cool to see that the hashing algorithm was easily kind of brute forced and gotten around. Now to move into talking about memory management and how that's implemented within the engine. So the actual storage and heaps and things like that. In general, I found that the engine used memory safe types, basically standard vector and standard map. They weren't really falling back on raw arrays or just mallocing raw chunks of memory, as you might see in a web browser. They're really falling back on these standard types, which have some implicit safety. You can't, access beyond the length of a vector. It'll throw an exception, for example. Found that array sizes were homogeneous. In contemporary web browsers, you often can do things like you can define like a uint8 array or a uint16 array or whatever it may be. You can have these arrays of various sizes. This has been a source of a lot of vulnerabilities, type confusions, or if you think an array is this long, but it's really int8s or something, it's much shorter, big overflows. Defender, as I said, implements roughly ECMAScript 3, so there really weren't these arrays of varying sizes. No optimizations that you might see in a modern browser for object getting and setting, just falling back on the standard operations like get this element from a vector, and they're actually falling back on the standard vector implementation of doing that. The one place I did see raw string buffers and raw buffers being just allocated was in JS buffstring objects, which store just a raw buffer of characters. But there are very few chances to have an arbitrarily controlled allocation size. The strings are generally capped in length at about, I think, 40,000 characters, far below even like int max or anything like that. No chances for overflows, anything like that. Heap management. So when you do allocations, when you create new objects, they get stored into this vector of JS heap objects. So this is part of that large JS runtime state structure that stores everything you need to know about the engine. And each time you do an allocation, they're going to append a pointer to this new allocation onto this vector of these heap objects. And this is actually really important because they can do cleanup at the end. They need to know where all the allocations are, where they've stored them. So they're just putting them into this vector and storing all the allocations they've made there. Now, garbage collection. So in this JS tree run function, I noticed this variable bool block GC. And this looked really interesting to me. I thought maybe I could find some vulnerabilities with the garbage collection, with the heap management. They have a mark and sweep garbage collector. So this is in the JS tree run function. Basically, after they run the statement, they'll do some garbage collection. Basically, it's a mark and sweep garbage collector, pretty standard, running through it, marking things to be freed, and then actually freeing them. And this caught my attention. Obviously, as I said, the JS tree run function can be invoked multiple times throughout execution. So for example, if you call an eval function or a toString, so this would be really great if you could have garbage collection of an object that was already allocated, maybe a lower stack frame had a handle or a pointer to it or something, and if you could get a garbage collected, this would be a great use after free. So I was really excited about this. And then 2 days later, Project Zero published some use after frees. So I was kind of disappointed that they beat me to it, but it was also cool that I sort of had the right intuition. They found like a bunch of use after frees. And Microsoft actually responded to this by removing the garbage collection entirely, which I'm going to show next. So I was really interested in how Microsoft had mitigated this vulnerability. They said it was patched, but they had found, I think, like 5 different use after frees in their report, and there are bound to be many, many more. So I threw this in bindiff and noticed a bunch of red nodes in JS run. And then zooming in on these, you'll see that they just knocked out the call the garbage collect sweep. So they just don't ever do garbage collection at all. They just took that entire chunk of code here and just like commented it out and removed it. I really hate memes in presentations, but I sent some screenshots of this to my friend at Microsoft, and he replied with this meme, which I had to throw in here. You can't ever use after free if you never call free. The thing is, they do have to free the code sometime. So what they do is just in the teardown for JS tree runtime state, or JS runtime state, which is basically this entire context for the whole JavaScript engine that's running. At that point, when they're destroying that object, when they're all done running your JavaScript code, they will then do a teardown of the JavaScript heap and just basically run through that vector and for each element free it. So there's no chance to use after free, again, because we're single-threaded. Execution is all over, and at that point, they can go through and pluck off these objects and free them. They're never at all freed, at least after the May 23rd build. They just are persistent memory during the time you're being executed, which only may be less than a second, and you're also constrained in terms of memory usage. So if you just blow the heap up and just do all these allocations, at some point they'll say, oh, you've reached your max allocation size, and they'll just kill your process and then go and free stuff. Pretty good for safety. Obviously, this will not work in like a real web browser, but for an AV that's going to run for maybe a second or two, I guess it kind of works. And easy way of mitigating use after freeze entirely by just never freeing anything. Talk a bit about the JS buffer string. I was interested in how these objects were stored because this is one of the few places in the engine where rather than just allocating an object, they have sort of dynamically sized allocations. And they'll actually allocate, like malloc a buffer and copy the string there. So I thought if I could find any vulnerabilities there, that would be a good target. So basically, JS buffer strings are these raw buffers of strings, and these chars arrays are used to back them. So basically what happens is you allocate this array, and then you assign it into your JS buffer string object. And you can see that here. They're doing the allocation, and then saying initialize this string with this buffer, and that's going to get copied in. And then I was auditing all the places that JS buffer strings are ever allocated and used. There are actually quite few of them. And in general, they're very secure and very conscious about the possibility for buffer overflows on the heap. Perhaps too conscious, because I found this funny bug that the escape function is actually broken as a result of being too security conscious. So if we pass in a single character to be escaped that actually needs to be escaped, so escape A, you can just return A. But escape percent needs to be escaped into percent and then some hexadecimal. So auditing how that worked, what they do is they take the size of the string passed in and multiply it by 3, and then allocate a buffer of that size. So for a single character, they allocate a buffer of size 3. Now, escape should escape, or this percent should escape into 3 characters, %25. That's a screenshot from Google Chrome. And what they do in Defender is they actually store kind of an index where if they escape the current character, the next character will go there. So if they escape this first character, or the 0th character in the string, the next character will go at index 3 in this new char array. And then they have a check that says if the index of the next character is greater than or equal to the size of the buffer they've allocated, they're going to stop, because this would be an overflow. But because we gave in a single character and they multiply it by 3, get the number 3, the index of the next character is 3, which is greater than or equal to the length of the allocated array. So they return early to avoid a buffer overflow. So escaping any single character element fails. This is just kind of a runtime bug. You could use it to detect the engine or whatever, but it was kind of interesting to see that. Here's a brief demo showing the escape function being broken. So we pass in escape, a string to escape, So %A, it escapes just fine. But when we do escape just the % nothing happens. It just short circuits. The entire statement is just finished. They don't even actually print at all. So this was interesting. Non-security bug, but fun finding that and auditing through the code to find that was broken. All right. And now to move into talking about fingerprinting and evasion. This is a particular interest of mine. I've done a lot of prior work on evading emulators. So I really have an eye for sort of these little tricks that you can use to detect and evade emulators. So I found a whole bunch of them. You could use them in this way to detect the emulator and then not run. So if you have a piece of malware, malicious JavaScript, or malicious web page, whatever it is, that's being run in here, you might want to say, if I'm going to detect Defender, I'm not going to run, else I'll run my malicious code. But you could also use it in this way, that you could detect Defender, and if you find you're running a Defender, you could then throw your payload that's Defender specific and exploit it. So there is some security implication to these. So just to run through these real fast. I found hard-coded values in the environment, so it's always March 19th, 2012. You'll find that the engine claims to be a Mozilla 5.0 browser. If you check document refer, it says you came from Google. There are some bugs where you can instantiate things that aren't really objects. There's no security vulnerabilities. You just get a raw, empty JS object structure. But this was interesting that you can create a new print or a new isFinite or a new eval. Again, it's just an empty object. There's nothing you can do with it interesting. And obviously, like in Chrome, if you try to create a new isFinite, you get an exception. So if you could do this, you might know you're running in Defender. And there are some typos. The collect garbage function, which actually doesn't do anything. It doesn't actually collect garbage, even when they had a garbage collector. There's a typo that they lowercase the c in collect garbage here, even though the function is uppercase. So just a very subtle thing. Whoever developed this, you could use that to detect that you're in the engine when you get this exception. Elements are typed as functions, where in like a browser, proper browser, they're typed as objects. If you check type of, it'll say it's a function. Found some weird things where they had multiple error handlers, so you can look at the string, and these strings are unique to Defender. The fact that they have these error handlers that say this function and that function are not defined or can't be used. And this is my favorite one, bug should never happen. I was working with sort of these type confusion, trying to find type confusions and things like that, and basically invoking HTML functions using things that were not HTML objects. So in this case, I took a number, and I was trying to invoke the HTML append child function, given a number as the this object to that call. And I found you get this exception, you have to pass in a DOM object, and then it says bug should never happen. So presumably this is from a developer who didn't expect this to ever happen. You can make it happen, but in their error message, they actually print out this string that is very clearly like a message to their QA people or whatever it may be. So that was kind of funny to find that. And then some other ones, like a parsing bug. You don't have to give semicolons between some JavaScript things like function.names not implemented, and then get time zone offset can be called with any type. It's not a bug, not a security bug, but it's kind of weird that they check the type for every other date function, but not that one. So that concludes the kind of reverse engineering portion of the talk. Just trying to cover everything I learned about this engine and how it works on the internal side. And I want to talk briefly about vulnerabilities within the engine and the attack surface left. So in May 2017, you might have seen these tweets from Tavis talking about this horrible bug that he found. This is what initially got me started in working on reversing this engine, got me interested in it. So I went in, and one of the first things I did when I was looking at this was try to understand the vulnerability, how it worked. So to walk you through that, basically their bug was a type confusion in JS delegate object error, toString. So you'll see some initial validation of whatever's passed in. It should be an error object. So they're initially checking that, is this actually an error? Then they're going to grab the this.message property. So they're doing a hash of message, grabbing whatever property is there. It's like a pointer to this object that they expect to be a string, and then passing it to this function that expects a JS string. This is actually one of those AV callbacks that's basically informing the AV side of Defender. You called .toString on an error. And then in that function that's called, they're going to treat the unvalidated pointer that was given that is assumed to be a JS string, they're going to treat it as a JS string without actually ever checking that it is a JS string. And then in JS string num bytes, which expects to take a pointer to a JavaScript string, in there everything comes crashing down because you can pass in, for example, a number rather than actually a pointer to a string. The way Microsoft patched this was just by adding that explicit type checking. So the value, the enum4 stands for JS string. So they just now explicitly check, is this actually a string before they run this function that expects to take a string on it. And just kind of looking at like the psychology of the developers and how this bug might have gotten there, they were using the .message property, and I noticed that that property is only ever used twice in the entire engine. The length property for arrays, for example, is used I think like 40 to 60 times, like very often. Message is only ever used during initialization of an error object and then during this one toString function. So it is kind of an obscure property, not used a lot, so might have slipped through the cracks from the developers and not done that type checking. I audited every other use of the getTypeValue function and of the JS object get. Couldn't find any other cases like this. So this is kind of unique, kind of one-off bug, best I can tell. And to talk about the overall attack surface, having spent all this time reversing the engine, obviously my purpose doing this was to find vulnerabilities. I didn't really find much. And I think why that is, number of reasons. So first off, the language. Complex ECMAScript features are generally avoided. So as I mentioned, things like array.prototype.sort are just not implemented. This has been a source of a lot of trouble in other JavaScript engines. So the Defender developers just didn't bother implementing it at all. A big attack surface reduction at the cost of breaking the runtime. Or, for example, the escape bug. They were so careful about checking never to have an integer overflow or heap overflow that they actually broke the runtime, but at least it's secure. In terms of data structures, as I said, there's very few controlled allocations. There's only one array implementation. You don't have multiple typed arrays. You don't have uint8 arrays, uint16 arrays, things like that. It's just array, and it just has a bunch of 32-bit values, pointers, whatever it may be. You have capped array lengths. They cap arrays, I think, at 40,000 elements. You don't have infinitely expanding arrays. You don't even have arrays that get close to int max or anything like that, or even like half of int max. There's some places where maybe they're doing an allocation, they'll take the length, multiply it by 2 or whatever. They don't even get close to int max or anywhere close to values that would be touching on integer overflows or anything like that. And also the use of standard library things like standard vector back in the JavaScript arrays, rather than actually using just raw malloc buffers. So there's a lot of implicit memory safety by just falling back on the standard library. It's not going to be super fast, but it's going to be clean and generally trustworthy. And implementation-wise, generally callbacks in the JavaScript runtime are avoided. So not a lot of chances to have a callback and change the state. The single threading makes this engine a lot more secure. There are a lot of places I found things that looked like vulnerabilities, looked like time of check, time of use things, but there was never a chance to have another thread change the state. It's all just single threaded. As I said, extensive type checking. I show all the different type checking that they have, the class types, the value types, so forth. No jitting, and then the biggest one, no garbage collection. Again, you can't ever use it for free if you never call free. If anyone saw Project Zero's blog about a month ago, it was about WPAD apocalypse. It was exploiting some bugs in JavaScript.dll in WPAD. Ian Fratrick does this listing of all these kind of attack surface reductions that it has, not necessarily intentional ones, but just sort of implicit traits of JavaScript.dll that leave it not very vulnerable because they don't have a lot of the complexity of a modern JavaScript engine, like Chakra or something like that. Defender has all of those same limitations, and on top of those limitations, they don't have a garbage collection, where they found a bunch of views have to freeze in JavaScript, and they also don't have array.prototype.sort, where Project Zero also found a couple bugs in that. So it's a very pared down attack surface. There's not a lot of places to go and try to attack. So overall, you have this sort of simplicity and ease of implementation over full implementation. They're taking advantage of being inside an AV, and they break the runtime in the interest of security. And hopefully this will be sandboxed soon, is the plan at Microsoft. So to conclude, what's in the remaining 98% of the engine, the other 43,000 functions? There are unpackers. There are tons of parsers for all kinds of formats. And most interesting to me, there's a Windows emulator. They have x86, x64, and ARM lifters that lift those assembly architectures into an integrated representation. And they have a VM that runs their IL. And they also have WinAPI and some NT kernel emulation, including a full emulated object manager. After wrapping up this JavaScript research, I dove into the Windows emulator, and I have a ton of material on that I hope to present soon. I was actually thinking about going to propose a talk for Recon Montreal all about how that works, and I've done even more work in there and built a lot of code around that instrument that just in the same way I've done with the JavaScript engine, but perhaps even more. There's also a Lua engine, which I started digging into. That is actually just for signatures. They write signatures in Lua. Don't bother wasting your time in terms of vulnerability research there, because you can't actually give any code to it. And in conclusion, it's a really cool target for reverse engineering. I learned a ton about JavaScript engines. I had never looked at one before, and just reversing this, I learned a ton. I hope to talk about the Windows emulator sometime soon. And then, custom tools are necessary to do this sort of research. And I think there's this perception of vulnerability. A lot of people tweeting like, oh, this is so bad, they have a JavaScript engine. But actually digging into it, I didn't find a whole lot in there. And I also want to thank all these folks for their help. There's my Twitter. I'm done. Any questions? Thank you.
Hello.
Hi.
I understood that the point of emulating this JavaScript was to detect new malicious JavaScript. But if it keeps crashes and doesn't implement a lot of function, how can it detect the JavaScript is malicious or not?
So I haven't really dug into the AV kind of classification of the scripts being malicious or not. I haven't spent a lot of time looking at how that works. I don't really know. My focus was on the actual just pure JavaScript implementation here. Evidently, it must do enough to be worth keeping around in the engine. I mean, even despite these vulnerabilities that were found, they haven't removed it. So there must be some value to Microsoft, but you'd have to ask a Microsoft employee how they use it and why, and if it's worthwhile. I guess it is.
Hi. So since you explored the sort function and the fact they don't actually implement anything with it, and I was just wondering, normally in JavaScript you can add a custom comparator function when you do the sort. Do they like completely drop that and let the JavaScript run? Because I'm asking because you looked at the sort function specifically. I was just curious.
So in the dispatch handler, when you call array.sort, they have a handler that's dispatched for any array method. This sort handler in a switch statement, it literally just says throw an exception. There's no looking at the arguments to give it into it. There's no checking whether you give a function or not. They just totally ignore the arguments. They don't care at all. So
it just let it run basically.
It doesn't care. It doesn't run anything. Yeah, it just immediately throws an exception.
Okay. Thanks.
Yeah.
Are there any more questions?
I think one over there. Or,
So you talked about fingerprinting the engine. So malware can detect whether it runs in Defender.
yes.
And you showed a wide variety of examples how it could be done. Do you expect Microsoft to improve the quality of JavaScript emulation to make fingerprinting more difficult?
So I did email MSRC like a month ago, letting them know I was going to present this. They said they had gotten my email and never heard anything more. This isn't particularly interesting relative to the fact like there's so many more higher priority bugs and just a million ways to detect these things. Anecdotally, a couple of years ago, 2 years ago, I did some work we called AV Leak, where we were looking at the Windows emulators and AVs like Kaspersky, Bitdefender, AVG, and some other ones. We presented a whole ton of ways of detecting those emulators, whether it's CPU red pills, timing attempts, whatever it may be. And when I followed back up with some of those emulators like a year later, a lot of the artifacts we presented like on stage at Black Hat were still there, and even really simple, stupid ones like just strings like the name of the program or the name of the username in the emulator, they were still there. So Anecdotally, seeing that presenting these sort of things, the AV industry doesn't seem to care that much. I mean, and making this thing high fidelity and hard to detect would be pretty hard, I think, and they have a lot more other engineering priorities, I'd imagine. So I can't speak for Microsoft, but I don't expect much in terms of fixing those detection tricks. Cool, thanks.